interlayer magnetic structure in the rubidium europium iron 4 arsenic 4, and this is quite peculiar material which has superconducting transition at temperature 36.7 Kelvin, followed by magnetic transition deep inside superconducting state related to ordering of European sublattice. It has a lot of very interesting properties, and in Argon we have a program developed around characterizing of this material, many peculiar properties. Of course, this program became possible because very nice single crystals was fabricated by Jinke Bao, this postdoc, in Mercury Canacesis group. It was thoroughly characterized in superconductivity magnetism group and resonance X-ray scattering was performed by Zahirullah Islam, and neutron scattering by our chairman. And most recent collaboration was with the University of Bath, where vortices was scanned using scanning hole probes measurements and superfluid density. This was the first talk in this session. And of course, this many interesting data motivated several theoretical considerations which are done by me in collaboration with Roland Villa. So my talk is organized as follows. First, I discuss magnetic singular superconductors and non-magnetic and magnetic 122 and 114 iron pnictides. Then I consider mechanism of interlayer helical state. I will consider normal and superconducting contribution to interlayer interaction and argue that this is the most reasonable interplay between this contribution is the most reasonable mechanism for emergence of helical state in this material. So the existence of magnetism superconductivity is a rare phenomenon. Nevertheless, in the past, there was several material was discovered where this coexistence does realize. First class of this material was discussed is in late 70s. It was rhodium barite with rare earths and so-called Chevrolet phases. For example, these famous plots show dependence of AC substitutability and resistivity for erbium rhodium barite. First, we have superconducting transition, and which is followed by magnetic transition, which eventually kill superconductivity, and there is very narrow range of coexistence of about half Kelvin when magnetism actually coexists with superconductivity. And about 20 years later, another class of magnetic superconductors was discovered, nickel borocarbides. In these materials, there are 4 compounds where magnetism coexists with superconductivity, and in contrast to these materials, magnetism actually do coexist with superconductivity, it doesn't kill superconductivity, even though it significantly suppresses it. Actually, people start to think about possibilities of coexistence of ferromagnetism and suggest superconductivity long before actual materials were discovered. There are 2 sources of interaction. There are, first of all, macroscopic magnetic fields generated by ordered magnetic moment, and there is exchange interaction between moments and Cooper pairs. And both of these mechanisms make impossible of coexistence of uniform magnetism and thin-layer superconductivity. This was actually pointed a long time ago by Vitaly Ginzburg in '56. And at least one of the states should become non-uniform. And first such non-uniform was suggested by in classical papers of Anderson and Schulz. They demonstrated that they proposed that actually magnet should split into small domain. This state is so-called cryptomagnetism. And size of domain is interplay between magnetic energy and superconducting energy. And this state actually exists when magnetic anisotropy is high, and when magnetic is almost isotropic. It was proposed that helical state is more energetically favorable. And if magnetic is hard and this deformation costs a lot of energy, superconducting state may become inhomogeneous instead. namely, magnets just generate a spontaneous vortex state in zero external magnetic field. This was also proposed long time ago. So material which I am going to discuss today is derived from so-called 1-2 compounds, which was discovered in early days of iron-based superconductors. The parent material for this are not superconducting. They have a spin density wave transition at 130 for this material at 135 Kelvin, but superconductivity may be induced either by substitution, by random substitution, or pressure. And there are many substitutions which eventually suppress spin density wave state and produce superconductivity. This has become big field by itself. Belonging to the same family, also magnetic superconductor. Instead of baryon, one can use europium, which has magnetic moment. And in addition to spin density wave state, there is also a magnetic transition related to ordering of europium moments in europium sublattice. Also, parent materials is not superconducting, but again, it can be driven to become superconducting by either pressure or multiple substitution on every side, on every atomic site. And most studied material in this family is phosphorus doped, when arsen is substituted by phosphorus. It's a very peculiar material. First of all, it's ferromagnet. In phosphorus substitution leads to flip of magnetic moment. It's oriented along the axis, and they show spectacular non-uniform state in agreement with early theoretical prediction. Namely, magnet splits into domain structure, where domain size and shape very sensitive to temperature. It means that it's joined by superconductivity, and superconducting state also become non-uniform. There is spontaneous vortices exist generated by magnetic moment. So it's combination of two theoretical prediction, theoretically predicted non-uniform state. Further develop, so all these materials I discussed so far are obtained by random substitution. But it occurs that it's possible to create also stoichiometric materials by substituting every second layer with either potassium or rubidium. Then we obtain so-called 1,144 material, which are stoichiometric and intrinsically hold up. They have superconductivity around 35 Kelvin. And again, there is a magnetic family of this one form was discovered. It was rubidium, europium, iron 4, arsen 4, or instead of rubidium also can be used cesium. So this material has very high, maybe highest in this family, close to 37 Kelvin, and followed by magnetic transition and 50 Kelvin, and it's lower than in paired material, mostly because distance between europium is twice as compared to parent material. It characterized by low anisotropy, and anisotropy factor is only 1.7, and quasi-two-dimensional magnetism, and magnetic transition is close to BKT transition. This explains this interesting king-like shape of a specific key transition. Later it was discovered that interlayer magnetic structure is kind of peculiar. It has helical shape. I myself learned this structure from my colleague Zahirul Islam, who performed resonant X-ray measurements, and later our chairman performed neutron scattering. Unfortunately, these argon data are still unpublished, and the main reason that was this Japanese group published a paper when they already obtained this structure by neutron scattering. So, and the main question is superconductivity responsible for such helix? This was actually proposed in this paper. And I see, in my opinion, that it's almost inevitable that superconductivity plays a role. There is a very simple argument. Helical state requires frustrated exchange interaction. It means that it's not sufficient to have only next neighbor interaction, next layer interaction. And distance this next neighbor, between the second neighbor, is already exceeds coherence length in this direction. This means that superconductivity strongly influences this interaction. It must play a role. And then the natural question is, mechanism is similar to this old mechanism predicted in this old classical paper. And the mechanism was that it was considered that magnetic moment and quasi-particles in normal region, it was supposed that superconducting state ferromagnetic and caused by RKKY interactions, and modification of this interaction in superconducting state leads to helical order. And even if this general theoretical picture is correct, theory still needs many modifications because of layer structure and open Fermi surface of this material. I briefly remind what is Ruderman-Kittel Kasuya Yoshida interaction. So this is interaction between magnetic moment in metals mediated by conductive electrons. Basically, one moment modifies spin density, which propagates over large distances, and the second moment fills this spin density. And this interaction is determined by non-local free electron susceptibility, and it has very famous celebrated oscillating shape, which decays slowly and oscillates with wave vector given by Fermi momenta along the direction of propagation. However, in this case, situation is totally different because we have open Fermi surface and we don't have actually Fermi momenta in the direction we are interested in the direction along the axis. The theory requires modification. So the model I consider Hamiltonian composed of superconducting part, which is located in iron earth layers, of magnetic part, which describes magnetic transition in European layers, and exchange interaction between these two. This is interlayer exchange interaction. The carriers moving in the iron arsenic layers field exchange field of European layers. And the peculiarity of the structure that interaction between European layers is mediated by tunneling between iron and arsenic. It's very important because the European layers coupled with different iron arsenic layers. So I consider simple case. I consider ferromagnetically ordered European layers and consider interaction between them. Then it's just given, the effective interaction is just given by sum of all exchange interaction over the European layer. Then in this case, the energy of spin configuration is given by effective exchange coupling, which is determined by effective susceptibility, which is integrated over in-plane coordinate. And this is a quantity which I am most interested in. And in our case, if you make very simple and invisible assumption that every European layer only interacts with nearest iron arsenic layer, then we have simple result that interaction between different European layers is given by this simple combination for interlayer susceptibility of electron. And so my purpose would be calculate this interlayer susceptibility, which determine both sign and range of interaction between different European layers. So I will start with normal state. So I consider simple spectrum, two-dimensional spectrum, and C-axis spectrum caused by tunneling. Then it's possible to derive very useful expression relating the interlayer susceptibility with two-dimensional density of state. And if we consider simple parabolic spectrum, there is immediate, we obtain from this formula immediate result that actually there is no interaction between layers in normal state. So the to have finite interaction, you need some non-parabolicity, which make two-dimensional density of state energy dependent, and interaction is proportional to second derivative of two-dimensional state with respect to energy. So the simple take-home message from this simple consideration is that normal state RKK interaction in layer system is ferromagnetic and short range, and this is already very different from classical textbooks result in three-dimensional material. Now I move on to superconducting state. So this is a result of derivation for superconducting state. We obtain the interlayer susceptibility, which is function of layer index, and some universal function of the ratio of Hopin integral divided by gap, which is actually approximately gives C-axis coherence length divided by interlayer spacing. And several important things, I would summarize several important things of this contribution. First of all, it's antiferromagnetic. It's always smaller than zero. If we fixed layer index, it's non-monotonically depends on the ratio. Actually, the next neighbor it reaches maximum when this ratio is about 2.4. And of course, at large distances, it decays exponentially, yeah, as you would expect in superconducting state. It's actually, nevertheless, if this ratio is large, superconductivity makes RKK interaction long range. It's kind of counterintuitive that actually superconductivity actually enhances interaction between layers rather than decreases, as one may expect. So we have two contributions. Normal part is ferromagnetic and short range, and the superconducting part is antiferromagnetic and long range, and this is create frustration, which may lead to helical state. And to demonstrate, I just performed simple illustrative calculation. I considered these two contributions. In the case when Hopin integral is bigger than a gap, this gives these two contribution to the energy as function of modulation of vector. And also I added anisotropy, which fixes orientation of the helix in the lattice. And this model gives the following phase diagram is in the parameter space. So the basic message that in certain parameter range we may have a modulation vector equal half pi, which is realized in rubidium europium 1144. So this model is of course illustrative and kind of toy because material is much more complicated and has multiple bands. And just to have a realistic model, we need basically electronic and superconducting properties of these bands. And we do have some information about superconducting properties. There is nice RPS data was published, so which gives gap values of this band. What's not available is we don't have experimental data for Hopin integrals, which is next important parameter in the model. So DFT calculation give the value from 10 to 40 millielectron volt, which is slightly bigger than gaps, and we can also get band average value, which is 12 millielectron volt, which is kind of in a good range for this theory.
There's only 1 minute left.
Sure, this is my last slide. So, I would suggest possible experimental test for the model. It's well known that it's established that the transition have strong pressure dependence. So magnetic transition increases with pressure, and superconducting transition decreases with pressure, and eventually they cross in the pressure of 5 gigapascal. The natural question is what is evolution of magnetic structure? So I would challenge experimentalists to address the question, and this model is correct. This would mean that when magnetic transition realized in normal state, it has to be ferromagnetic. This would be simple test of the theory. So in conclusion, so we investigated interlay and interaction, normal state, ferromagnetic and short range, superconducting state, antiferromagnetic and maybe long range if Hopper integral exceeds gap. And I believe this is most likely mechanism for helical magnetic structure in this material. Thank you very much.
So what would you expect for the helical structure if you apply a field parallel to the planes?
Transition to double periodic structure, phase transition to double periodic structure when spins in two layers tilted at one angle and spins in two angle tilted at other angle. And eventually, of course, it should saturate a certain field.
When I shortly interpret your last summary, that pi over 2 helix is a result of the compromise between the normal ferromagnetic type interaction, which tries to set the parallel orientation, and the antiferromagnetic pi orientation in the superconducting state. If this is correct, then in this inequality, delta is a function of temperature. So would I expect to that helicity angle may change as a function of temperature?
Transition temperature approaches magnetic transition. This probably would be correct. I would think definitely in pressure, when magnetic transition come closer, you would expect that Q vector would be bigger and bigger. This is theoretical expectation.